Okay, so I'm Jared. Fabio was supposed to give the talk today. Unfortunately, he's based in Italy, and because of travel restrictions, he wasn't able to come today. So he was really gutted not to be with us today. So anyway, I better do a good job for him, or else he's going to be really angry with me. So quick talk outline, quick motivation, why do we care, who or what is DeVito. I think GPU support we want to highlight. I think that's the big difference between last year and this year. And those that were here last year, you'll know that we announced MPI support, so finally GPU support. What our roadmap is going forward, we're by no means finished. We have a lot to do. And closing remarks and acknowledgements. Okay, that doesn't work either. Phew. Okay, this is not going to work. Can we resize something? But it's also most of the presentation is missing. There we go. And then page down now works. Should work. Okay, motivation. Well, if you don't recognize this picture, you're probably in the wrong room or conference. And so basically, what's our target application? Well, it's all compute intense stuff. So with Philip's talk earlier on, it was they're the guys that do the FWI and RTM, and then the workhorse that's actually doing the computation, heavy lifting for doing the wave propagation or for doing the gradient calculation is DeVito. That's its job, to try and do that very quickly. From my perspective as a computational scientist, background in physics and supercomputing, this is a really cool problem to work in because it's just insanely computationally expensive, data intensive, everything intensive. So there's a lot of concerns here in designing good technology around this. For the industry, it's about reducing the cost of modernizing software and exascale for the cloud because it's not good enough to have a good production code today. You need to have one tomorrow, whatever hardware and architectures are coming down along the line. And when you keep an eye on this requirement for continuous innovation and keeping up with technology trends and new algorithms, you have, like everyone is struggling with the skills gap. Like there isn't that many like geophysicists who are also like superhero data scientists and HPC developers. So actually just moving the technology forward, these are all concerns. And particularly as well, we're all looking at AI and machine learning and figuring out, well, how can we exploit all of these as well in the workflow, maybe designing some hybrid solutions around this. But again, can we take our old legacy codes and ram it into a machine learning framework? And very often people's answer is no, they can't. So let's go into, that gives the background, the motivation, the context, why we want to develop DeVito. So the traditional approach to developing software in this area, if we just focused on the bit that calculates the propagation or the PDEs or the gradient calculation, is we start off with our PDE, whatever that is, and we hand it over to really smart people who generate impenetrable code developed by rock stars, ninjas, gurus, or whatever we call them these days. And this is problematic then because very often your rock star that's doing the low-level optimization is not the same as a rock star who actually knows the physics and knows the geophysics and knows what problem they're actually trying to solve. And this also kills off your innovation cycle very often because the geophysicist hands over their nice code where they understand the algorithms, it gets optimized and they can't understand what comes back. So we don't want to do that. And the solution, there's a saying, and I forget offhand who said this, someone will correct me now in a second, but there's exactly one trick in computer science, and that is to raise the level of abstraction. So the whole philosophy and design around DeVito is basically defining DSL, so that's domain-specific language. So before anyone else asks, no, DeVito doesn't do finite element or pseudospectral or anything else, because that's what the domain means in domain-specific. It does finite difference, and it does it extremely well. So what you have there in the middle then is you basically providing it a mechanism to write equations that look like the actual PDEs that you have in your paper there. And then the compiler takes over then and it's able to synthesize that information and says, okay, well, I know you're trying to solve finite element. You can provide the specification about the mesh and whatnot, and it's able to generate all of the mathematics and algorithms that you require. And that generates all of the impenetrable code for you. So like what does it consist of currently? Well, as I said, it's a DSL compiler for explicit finite differences. Explicit just because that's what everyone was asking us for, even though there's work in the pipeline for implicit support as well. It's a Python package, like Python API, and that doesn't mean it runs slow like it's a compiler. So we're generating low-level code at runtime. So that's basically C, like typically C99 standard, SIMD, OpenMP, MPI5 offloading. I think right at this moment I could ask George and Ken what the state of OpenACC support is. And then in terms of architecture support, x86, we still have lots of people asking for support and optimization on the KNL. And GPUs, like the announcements really now for today, ARM64, Power 8s, Power 9s. And so it's very easy for us to support all these architectures just because of overall design. Composability is a big issue here. So, and I think this is where, like initially we were always trying to sell DeVito for, yeah, go performance, like stuff will go really fast. In actual fact, we found it was more popular just because people could easily integrate it with existing tools, and particularly like without any effort they could use it with PyTorch or TensorFlow and these other tools to do data science games. It's open source, so we want to be industrial friendly, so we took a very liberal MIT license. So you can go do whatever you think you want with it. And really key for us is also best practice about software engineering. So I loved the talk yesterday from ExxonMobil where they were talking about DevOps. So CI/CD is like central to what we do. We've got extensive testing in the code to make sure that we get that we always have correctness. And that includes like code review. So like everyone has to, every commit is actually reviewed by other people on the team to make sure that it's up to scratch. And that's after it passes all of the tests and CI/CD. And cloud ready. So like a big advertisement for Wednesday, am I allowed to do this? Like, turn up to our workshop. And we also have a hackathon in the afternoon to play around with GPUs where we have everything already deployed on the cloud. So you get your own cluster and your own nodes and everything to develop on. Okay, I can go through this, but then I'm watching that I'm going to lose out of time. Is that, yeah. So basically, just to give you an idea, like we have got a growing community, which is great. To give you an idea of one of the reasons we can make such big progress here is the core compiler itself is 17,000 lines of code, and that's a compiler. Now, bear in mind that with that 17,000 lines of code, we have like everyday acoustic solvers, anisotropic acoustic TTIs, elastic, viscoelastic. We have guys using it now in civil nuclear engineering, CFD, and other areas. So that's what we get for our 17,000 lines of code. The other thing I want to draw your attention to is that we have 17,000 is lines of code in the compiler. We have got 9,000 lines just of testing code, unit testing code. So this is what I meant by the importance of DevOps and testing. We've got extensive test coverage. I think it's about 90% test coverage at the moment. And we've got extensive tutorials and so on and so forth. And then we have got an open source consortium. So I think one of the things that I'd like to highlight about this is open source is still not a thing in this community. It's like people are still very nervous about open source. But like we were happy that like BP, Doug, Microsoft, and Shell, so they're at the moment they're funding this as an open source consortium. So they're not saying like, what do we have for our money? Like the point is that they're giving us a core support so that we survive. And it's been quite exciting working with Doug. So they're really the people that forced us to bring this from being a research code into actually something that was being used like in a production environment. So they basically shouted at us for 12 months until it did everything that they needed to do for production. And yeah, so there are just some statistics. We got about 270 people on our Slack channel and about 90 different companies and research institutions. So GPU support without the excruciating pain. To understand first, I just want to give you a view of the compiler so you'll know why it's possible. And it's just to highlight that it goes through these multiple stages. So there's no magic in here. There's no source translation in here. You're basically going through a series of steps from the Python where you have explained what equations you want to solve. And then you're lowering it down into stencil operations. Then you're clustering, you're gathering together things that look the same. You're trying to detect aliasing. You're trying to detect what can you pre-compute and cache and use it later. Factorization, you have blocking, fusion, fission, as the case may be. And treeification then is basically turning that into an abstract syntax tree. So all of this is textbook compiler stuff. This is how a compiler is designed. And then at every stage, you're bringing it closer to code, and you're reasoning about the code, as in what all your data dependencies are, what can be executed in parallel, what can't be. And then at these different stages, then you can start making different decisions depending on whether you've got a GPU backend or whichever architecture you're interested in, because you always want to do slightly different stuff. Until you get down to the beginning, to the end here, where you have just-in-time compilation for use. So I couldn't do a demo today just because we preload the stuff, but this is the type of stuff that this is the type of code that you might generate if you're targeting OpenMP5. So it's identifying the loop, is identifying what data needs to be offloaded to the GPU. I've included a link there if you download this. We have got a Jupyter notebook online with just a simple diffusion equation, just so you can play with the Jupyter notebook and see exactly what it does and how it works. And basically that is the trick, as it were, that allows us to support multiple different backends. In terms of performance, so the caveat here is we have done no performance optimizations at all yet. Literally this was released last week. 90% of the work, or 95% of the work, was only re-engineering the back end, just to give us the flexibility for targeting different architectures. But still, off the bat, we were already getting performance for those two benchmarks, where it was going twice as fast as the CPU. Now, and that includes source and receiver terms, so your sparse operations, not just the stencil propagator. So twice as fast as, of course, we know that it can be made go much, much faster. But then the whole point of tomorrow's workshop is that we actually set up then a sandbox where the source code is actually generated. And at that point, then you can get the NVIDIA gurus to say, OK, what do you need to modify in this particular stencil and to make it go faster? Then we can benchmark it. And then once you have a diff between here's your reference implementation and here's your tweaked implementation, you know how you need to augment the compiler to learn that trick, as it were, and then to move forward. So join us tomorrow. It should be great fun. MPI support. So while we have MPI support for the CPUs, we have no MPI support yet for the GPUs. But hopefully, we're hoping that's relatively straightforward. But the key thing here is no changes are required to the user code. So both in these cases, whether you're talking about CPUs, GPUs, or using MPI, no changes have to be made to the user code. So basically the code that the geophysicist is going to write. All of this is happening under the hood. And so what does our roadmap look like? So the JIT backdoor we think is really, really critical, because that is basically what means, that means that the veto is not a black box. It's giving you a mechanism where we generate the code. We go to great lengths to make sure that the automatically generated code is human readable, specifically because humans typically have to edit it, to hack it, if we want to extend it, it can be very difficult to figure out what pattern should be including in the compiler here. So by doing it this mechanism, the gurus can go, they can make the changes to the code, and then we can say, okay, that's what you're trying to do, and then we can learn it into the compiler. So we find that's really important, and that's what we're going to be exploiting in the hackathon tomorrow as well for furthering GPU support. So MPI obviously important for the GPU for multiple devices. Like NVIDIA was also recommending that we should actually consider UCX instead. There's no reason why we shouldn't use both, so we might also try to work on that tomorrow. I loved seeing Frank's talk. I didn't realize he was speaking today, but we're huge fans of velocity compression and optimal checkpointing strategies. So hopefully we'll talk to you more later. OpenACC, again, this is because of the strategy, it's very easy for us to flip from one parallel programming model to the other. So that's work in progress. So hopefully we'll have something landed in the next week for that as well. Performance optimizations, other backends. So Intel is interested in 1P API, CUDA, and so on. On our hit list. Conclusion. 3 minutes to go. So I think the Vito, what we're trying to do really is to bring two things together, and that's high productivity, because humans are your most precious resource, and high performance, and bring these two things together. So it's driven by both commercial and research demands. Our industrial advisory board is in effect the Vito consortium. So that we try to remain relevant. And then the key thing here is that it is an actually compiler. Like that's what it is. It's designed as a compiler. The guys behind the architecture, they have PhDs in writing compilers. That's what they do. It's not the source-to-source translator, which a lot of other tools in this area that might look similar. They're actually just source-to-source, and they're not able to do the same type of sophisticated analysis and to figure out how to optimize the code. We have a growing community of open source contributors as well as commercial users. And a general request here is, we are always meeting loads of people that tell us that they're using it heavily internally, and we just hear, like when we meet them informally on the floor, but they never actually reach out and interact with us. So like say, if you're those people, like I'd encourage you to please engage with us, because we'll do a whole lot more if we work together. And the key point is, this is not sort of singing kumbaya together. It's a simple fact that this is a well-recognized like a business strategy these days. And finally, acknowledgements. So huge thanks to our sponsors, particularly Microsoft, giving us loads of credit that we're very busy burning at the moment. And then in particular then, there's quite a large bunch of people behind this. I marked all the guys in bold there who are here for the conference. They'll be around as well, both at the posters and at the workshop tomorrow. So I hope they got them credit. Philip Witt, congratulations. He graduated his PhD 2 weeks ago. He's looking for a job. Grab him while he's still available. And if you want to see a full list of contributors, like we want to make sure everyone gets the credit they deserve, you can always just check our releases. So we maintain a list of contributors on each release. And that's it. Thank you very much.
Going back to some of the example code where you're showing u equals time function. So for elastodynamics, we don't have u as a scalar value. U is typically a displacement vector.
Yeah.
Can I give it a vector value function in there? Du by dt or d squared?
Thanks to Matthias Lebalton, who's here. Also graduated last week. He added a really nice feature for tensor support. So pretty much specify things as any tensor that you want. And then it's nice then, because then at the abstract layer it's nice, elegant from the mathematics, because now it looks like the abstraction is perfect and it all comes out. And then of course, then once you have expressed everything in tensorial form, you can then optimize the hell out of it, because all of the vectorization information is inherent. Exactly. Stunned silence. Okay.
Thank you much.
Thank you.